Hello, I'm Rohan Prabram, and this is my Physics 2212 Lab 4, Magnetic Braking with Faraday. Our purpose is fourfold. So first, we want to measure how an aluminum foil tube shows a falling bar magnet via induced eddy currents. Second, we want to record 5 drop times and compute the average transit time, which is delta t experimental. And third, we want to build a VPython dipole tube model and extract the simulated transit time, delta t simulated. Finally, we want to compare delta T experimental against delta T simulated as a test of Faraday's law and Lenz's law. Now, looking at our procedure, we begin by assembling the tube. Wrap 2 layers of aluminum foil around the cardboard core and measure its dimensions. The tube length L is 0.253 meters. The inner radius R in is 0.013 meters, and the foil thickness T is 0.0174 meters. Next, we mount the tube vertically on a non-magnetic stand and frame the entire tube in the camera. We mark the North Pole above the tube opening without touching. We record high-speed video at 240 frames per second, release the magnet smoothly, and let it fall freely through the tube. From the video, we note the entry time T enter when the leading edge crosses the top lip and the exit time T exit when it leaves the bottom lip. We repeat this drop 5 times and we compute delta T as T exit minus T enter. Now, looking at some key concepts. Our first is the magnetic field of a dipole. Our bar magnet at vector r is B of r equals mu 0 over 4 pi divided by r cubed times the quantity 3 times mu dot r hat times r hat minus mu. Second, Faraday's law of induction, which states that the electromotive force epsilon equals minus the time derivative of magnetic flux d phi by dt, which derives a ring current I equal to epsilon divided by the ring resistance R. 3, Lenz's law tells us the induced current always flows to oppose the change in flux. And fourth, Newton's second law applies to the falling magnet. M times acceleration equals the sum of gravitational force and magnetic braking force. Now, looking at our experimental data and results, in our experiment, the tube dimensions are L equals 0.253 meters, R in equals 0.013 meters, T equals 0.0174 meters. The 5 trial times in seconds were 1.82, 1.81, 1.79, 1.88, and 1.88. Computing the mean gives a value of 1.83 seconds with a standard deviation of 0.038 seconds. Now, looking at our simulation, our VPython model represents the magnet as a point dipole with moment mu equals 1 ampere meter squared and mass m equals 0.023 kilograms. We divide the foil tube into rings, each with resistance R equal to resistivity times 2 pi times radius divided by thickness times segment length. These are the results. So running the simulation produces a velocity versus time plot and prints the simulated transit time. We find delta t simulated equals 1.728 seconds. For comparison, the ideal free fall time through 7.253 meters is 2t free equals square root of 2L over G equals square root of 2 times 0.253 divided by 9.81, which evaluates to 0.228 seconds. Thus, both experimental and simulated times are roughly 8 times longer than free fall, confirming strong magnetic braking. Now, some assumptions. We've made several simplifying assumptions that the magnet is an ideal point dipole, the foil rings are uniform and axisymmetric, and we neglect air resistance and friction. Major sources of error include timing resolution, which is plus or minus 1 frame at 240 frames per second, variations in foil thickness that alter ring resistance, edge effects at the tube ends that break axis symmetry, and possible magnet tilt or off-center drops. So, to conclude, our measured average transit time delta t experimental equals 1.836 seconds, and simulated transit time delta t simulated equals 1.728 seconds, are in agreement within 6.2%. Both are much greater than the free fall times of 0.228 seconds, demonstrating that induced eddy currents produce a significant upward magnetic force that opposes gravity. For further study, one could use copper foil of lower resistivity to increase braking, cut longitudinal slits in the tube to disrupt eddy currents and speed the fall, or vary the magnet's dipole moment and foil thickness to explore parameter dependence. Thank you.